Hi, today we're going to take a look at some special trig functions when it comes to finding their limits. So yesterday, and we've been reviewing some basic limit rules, remember that the limit tells us what a function is approaching, and that's the big thing right there. This is not the value of the function itself, but rather what the value of the function would be if we could substitute in, and that's the big thing about a limit. If the limit of a function equals the value, again, we say that this function is continuous at that point. Ideally, we would get a value when we substitute any number into a function. For example, let's take a look at the function sine of x. We can plug any number into the domain of x and get the value of x. For example, if we let x be 0. Well, f of 0 would be sine of 0, which is 0. Notice we get a value. So, what would the limit as x approaches of 0 of sine x be? Well, of course, that would also be 0. We would say that this function is continuous at x equals 0. However, as we can recall from last year, not every function has an infinite domain like sine. Let's look at the function sine of x over x. What would happen if we plugged in x equals 0 here? Well, we would get sine 0 over 0. So we would get 0 over 0. And we already said that this is bad to have, that this is indeterminate. And in other words, at x equals 0, we don't know what it is. That the value itself does not exist. So that's what it means to be indeterminate. Let's look at the graph of sine of x below. Well, so it doesn't mean that we can't approach something. For example, if we look at the graph of sine of x over x below, what can we say the value approaches as x gets really close to 0? Let's see here. Well, if I approach from the right side, it looks like the value is approaching 1. Be careful of the scale. And if we approach from the left side, it also looks like we're approaching 1. So we could say, well, we can say that the limit as x approaches 0, because remember that's what this is, right? This is what's called a limit because the value does not exist, right? Because the value, right, does not exist, we must use limits. So in other words, since the limit as x approaches 0 of sine of x over x is 1. In other words, this is saying that the value approaches 1 right there. Today, we're going to discuss this special rule and other special trig functions algebraically. We will have to get creative, right? We are too young right now to understand this. Understand how these three rules came about to be. We're going to discuss that later on this year. So let's see here. The special rules for trig. 1, sine of x over x, the limit as x goes to 0, notice where it has to approach 0, because this gives me 0 over 0, this is 1. That's just the rule that we're going to memorize. Tangent of x, again, there should be an x there, 0 over 0, tangent 0 over 0, I get 1 also. And the other one, the last one, the limit as x goes to 0 of cosine, 1 minus cosine of x, that's just 1 minus 1, which is 0 over 0. This limit is 0 itself. We can also talk about some reciprocals. For example, if I take the limit as x goes to 0 of x over sine of x, this is 1, sine x over x is 1, so if I flip it, I still get 1. However, if I flip the cosine one, x over 1 minus cosine of x, well, if I flip this right here, I would have to flip my answer. 0 over 1 is 0, but 1 over 0 is undefined. It does not exist. These are sometimes called the reciprocals. Okay? All right, so let's take a look at some examples. I think some of you guys will really like this lesson right now. So we want to memorize these rules right here. So let's use them. Okay, the first one. Number 1 up here. Let's take a look. For the first example, what we want for sine of x over x, we want either sine x over x or x over sine x. Those are the two that we want the most of. So if we take a look here real fast, I almost have that right here, right? But the problem is these two values right here, these have to be the same, and right now they're not the same. So the question is, how can I make them the same? Well, one way I could do it is I can think of this 4 as a constant, and I can factor that out, and that's going to give me the limit. Whoops, sorry, let me pull that 1/4 out. Times the limit as x approaches 0 of sine of 5x over x. Now, you might be like, but Mr. Warnow, these aren't the same. See, the rule here is, these have to be the same. The x values have to be the same. And right now, this is a 5x, so I need this bottom now to be a 5. Well, how can I do that? Well, I can just multiply top and bottom by 5. Just this part. Just this part. And then what I'm left with is 1/4 the limit as x goes to 0 of, pull the 5 out to the front. I'm going to see the bottom is what I want. I got that 5x. I already have that sine of 5x on top. The 5, that's extra. I had to have that because of algebra. By multiplying the bottom by 5, I have to multiply the top by 5. So this top 5, I just bring down and multiply to the outside there. And what I'm left with here is 1/4 the limit as x goes to 0. Whoops, sorry. Messed up there. I can actually just go really straight to my answer now. I got the 1/4. Well, the rule here is that, well, sine of x over x. That's what I have here. Once these are the same, that's like saying sine x over x. Doesn't matter what's in front of it. This is just 1. That's a rule. Times that 5. And I just get 5/4. If we take a look at an example like number 2, again, if I try this one, well, I can split my fraction. Again, if I try it, I get 0/0. So for this one, I am going to split my fraction. I'm going to write it this way. The limit as x goes to 0, 2x over x plus sine x over x. Now this is where we get to dangerous mathematics, right? I already know that this is just 1. Right there. But if I plug the 0 in right now here, I'm going to get 0/0. And we don't like that. We can't ever write 0/0. So use algebra. Cancel those out. And what I'm left with now is just 2 plus. And I can add those now. And that's just going to give us 3. So this limit right here is 3. Alright, for number 3 here, again, remember, we want sine x over x or x over sine of x. So for a problem like number 3 here, well, oh look, remember, we want these x values to be the same. And notice on the bottom I have this 2x. So this 2x and the sine of 2x, they're almost the same. So I'm going to kind of split this up using multiplication though. The limit as x goes to 0 of 2 over sine of 2x times sine 3x over 1. Now I just need to think what the other one needs. For example, for the first one here, if this 2 had an x on it, it would be good. This one needs an x. In order for me to use my rule for sine x over x to be 1, right here, I need here a 3x. And that's exactly what I do. So for the first one, I'm going to multiply the top by x. That's going to take it to 2, so I have to multiply the bottom by x. For this 3x over here, for the sine of 3x, I need to multiply the bottom by 3x to get my sine 3x over 3x, and I multiply the top by 3x. And I just match up their like part. I want this x to go here, and this 3x goes to here. And then I can just write out what I have left. The limit as x goes to 0. This becomes 2x over sine 2x times sine 3x over 3x. And don't forget, this x and this 3x are left over. So I got this 3x over x. and then I'm ready to get my answer. Well, this term right here, sine 2x over sine 2x, that is 1 times sine 3x over 3x, that's just 1. But what happens here, again, don't plug in 0 before you cancel. Cancel those x's first, and I'm just left with 3. And my answer here is going to be 3. This is probably the hardest one there is, so you may want to go back and watch that one again. Right. For number 4, again, I want sine of x over x. And oh, do we see that? It's kind of hard to see, but on the bottom, I can factor an x out. And I can then rewrite this as the limit as x goes to 0, sine of x on top, and on bottom I would get x times x plus 2. There's my sine x over x, that's what I want. So we get the limit as x goes to 0, sine of x over x times 1 over x plus 2. Right here. And I'm pretty much done. Ready? We already know that sine of x over x, that's just 1, times, if I plug the 0 in here, I get 0 plus 2. So I get 1 times 1/2, which is just 1/2. And there's our limit right there. Okay, we're going to go and stop the video right here. Go into part 2. We'll talk about something called the squeeze theorem. Now, the squeeze theorem is one of the ways that we prove up here, and we'll see some examples in just a few moments.